Modern web applications are strictly decoupled. The front-end interface and the back-end database operate as separate entities, communicating across a digital chasm. To function at all, the client has to request data from standalone microservice APIs. Suppose you are building a dashboard. You need to initiate a network request to pull the current user's private profile data from the server so you can display it on screen. Looking at this code editor, you write a standard fetch request. Because you are asking for private data, you add the Credentials include flag. This instructs the browser to attach the user's session cookies, ensuring the server knows exactly who is asking. On the server side, you want to guarantee the front end can access the response. You configure the cross-origin resource sharing headers, setting the access control allow origin to the global asterisk wildcard. You are explicitly telling the server to permit access to any requester. You run the code. Instead of loading the profile, the browser forcibly terminates the connection. A massive red CORS error blocks up your console. The browser's internal security mechanics have deliberately intercepted this request, treating the specific combination of a wildcard and credentials as a hostile act. Every front-end developer has fought with CORS errors. When a request gets blocked, the immediate temptation is to bypass the friction by throwing a wildcard on the backend to get the data flowing. Placing an asterisk in an access header sends a very specific message to the network. It tells the browser that the server has enacted an absolute abdication of access control. That open door policy collides heavily with the mechanics of session cookies. When you ask the browser to send user credentials, you are introducing highly sensitive state into the pipeline. The browser does not blindly trust the server's instructions. It acts as an autonomous firewall, independently evaluating the mathematical safety of the transaction. Combining the wildcard's implicit trust with the explicit risk of user credentials creates a systemic paradox the browser refuses to compile. To see exactly why the browser rejects this, we have to look at the foundational security bedrock of the web. Browsers are inherently hostile environments, executing untrusted code from servers all over the world. This illustrates the primary defense, the same origin policy. It places an impenetrable barrier between domains, preventing data flow. An origin is defined by three components: the protocol, like HTTPS, the domain, and the port, like 443. If any element differs, the wall locks down communication. The same origin policy guarantees that a script loaded on one origin is completely blind to the data housed on another. A script running on a news site cannot read your banking tab. This creates severe architectural friction. Modern distributed web applications rely entirely on cross-domain APIs. The same origin policy is the necessary prison that keeps the internet secure, but our architecture demands a controlled method for breaking out. CORS is the standard protocol for puncturing this barrier. The browser attaches an origin header to the request, identifying it. The server evaluates this, responding with the access control allow origin header. The browser verifies the match and allows the payload across the chasm. This brings us to the actual, valid use case for the wildcard. If a server is distributing purely public, unauthenticated assets, like web fonts or weather data, the asterisk tells the browser it is safe for anyone to read the response. Public resources operate under different rules than private resources. The threat model changes completely the moment a specific user is identified. CORS operates as a strict opt-in protocol, where servers must explicitly lower their defenses for specific verified callers. To construct the exploit, we have to look at client-side state. Cookies are the mechanism the browser uses to establish and maintain your authenticated sessions. The browser performs a critical automatic behavior. It faithfully attaches your unexpired cookies to any outgoing network request destined for that cookie's specific domain. Assume you are currently authenticated with a secure API. In another tab, you navigate to an entirely separate malicious website. That malicious site executes JavaScript in the background, firing a hidden fetch request directly at the secure API. It is attempting a cross-site request forgery. Because the browser automatically attaches your session cookies to that background request, the API receives what looks like a perfectly valid authenticated call. If the API's response includes a wildcard, the server processes the data and sends your private information straight back to the malicious origin. Without extreme browser intervention, the combination of a wildcard and automatic credentialing transforms a simple API into a massive data leakage pipeline. Now we return to the exact moment of the fetch error from our initial setup. In that scenario, the server actually received the request. It processed the credentials, executed the query, and sent the sensitive payload back over the wire. But the browser intercepts the server's response before the JavaScript engine is allowed to read a single byte. It evaluates the transaction against the W3C specification. It spots the credentials include fly. It spots the wildcard response. It registers a critical spec violation. The browser actively destroys the response payload in memory and throws the CORS error to the console. This console error represents a successful interception, effectively neutralizing a high-risk data breach before the payload ever touches the application layer. To fix this, you have to architect an API that accepts credentials securely without triggering the browser's veto. The first requirement is that the server must completely abandon the static wildcard for any authenticated route. This diagram outlines dynamic origin reflection. An incoming HTTP request arrives, carrying a specific origin header. The server must programmatically extract this origin header. Then comes the validation phase. The server compares this extracted origin against a strictly maintained whitelist of trusted domains. If validated, the server dynamically echoes that exact specific origin back in the access control allow origin header. It then adds the final mandatory header required by the browser specification to unlock the data, access control allow credentials set to true. The browser evaluates this new precise pairing of headers. It verifies the explicit trust and finally passes the JSON payload to the front-end code. Modern web security demands explicit, verified trust at every network boundary, ensuring that private data is only accessible to authorized origins.